All right, our next general chapter in the USPNF and the CTC 115 class is 781. 781 is called optical rotation. So, if you've had organic chemistry, you have probably, at least I hope, have seen optical rotation. But the problem is that if you're taking 115 in the order that you're supposed to take 115 in the chemical technology program, you've not made it to organic chemistry yet, even if you're going to take the organic chemistry class. So I am preempting the optical rotation lecture before you make it into that class. So good news for you. You get to hear it from me first. And then you're going to go into organic and you're going to be like, I'm a pro at optical rotation. Give me my A today, please, because I don't even need to sit in this lecture today. All right, so that's what we're getting ready to talk about. And before we do, I'm going to show you 781 optical rotation. So it looks like in General Chapter 781, they give me a little bit of introduction, and it's, oh gosh, equations, and then numbers and letters and variables, and gives me some more definitions of things. And as I scroll down, oh no, specific and angular rotation, what are those things? So we're going to take this little bits at a time. And the very first sentence up here that says, many pharmaceutical substances are optically active in the sense that they rotate an incident plane of polarized light so that the transmitted light emerges at a measurable angle to the plane of the incident light. So literally what they're telling you is that in the pharmaceutical environment especially, we have these compounds that take incoming light, and that incoming light is directed in one direction. And these molecules take that light and it begins to rotate it. It begins to turn it. And that's why we call this optical, optics for light, and rotation because it will rotate that light. And it could rotate that light left-handed or right-handed. So two different directions, just like a clock. We can go clockwise or counterclockwise with it. So left-handed and right-handed. All right, so that's where we're going to start this discussion off as far as optical rotation goes. So optical, once again, is referencing light energy, and we're going to have a source of light when we make these measurements. And rotation is about how does it turn. So we're going to have an instrument or manually do it, but an instrument's still going to be involved in some form or fashion where I can measure how far do I have to turn it in order for this to kind of work. So do I go left-handed or do I go right-handed? And then if I go left-handed, how far of a turn do I need to make? If I go right-handed, fine, but how far of a turn do I have to make in order for this measurement to make sense? So we are looking at literally the turning of light that is due to the molecules that are present in the sample. And one of the drastic things that you need to remember, ding, 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 that's going to be a question, is that not everything is actually optically active. All right. So some things are, and many things that we work with, especially in the pharmaceutical industry or maybe even in the food additive ingredient industry, those could turn light left-handed or right-handed by an order of magnitude. But not everything does. Even maybe some complicated looking molecules and structures, there's a chance that that might not rotate light either. So we're going to have to figure out, like, can we predict it? Can we look at a structure and know, is it going to turn or is it not going to turn? Right? Because if I know that it's not going to turn, then I'm probably not going to do an optical rotation test. And the reason is because it's not going to do me any good. So if I'm doing this test, I'm assuming that the sample is going to rotate light. So in a typical run-of-the-mill lab environment, if I am performing 781 for optical rotation, then that probably means that someone has already determined that this particular molecule does turn light in a certain way and a certain direction. So that's great. I just need to go through the motions. I need to do that test, and I need to record that value. But I also need to understand that not everything is appropriate to run on an optical rotation device that we call a polarimeter. So polarimeters are great. Polarimeters are used for many things, but polarimeters are not going to be universal because not everything rotates light at all, okay? A couple of other things about optically active. Some compounds rotate light. Ding, 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 ding. I've already told you that's probably going to be a test question. And they will rotate light clockwise, and we use a positive symbol for that. All right, so clockwise, of course, means here's the clock, and up here is number 12. So if it goes to my right hand, tick, 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 and then around, that is clockwise, and that direction is going to be a positive direction. But if I'm left-handed, and I am left-handed, so this is sinister people, the child of the devil, maybe, right? We have negative values, and that's because it goes counterclockwise. So if I start up here at the top, and this is the 12 mark, and I go to my left hand, that is going backward on the clock. So this is our negative rotation, and this will be our positive rotation. Molecules can rotate light positive or negative. And actually, we don't really know which way they're going to turn the light. There's no way that we can look at a structure and say, yep, this is going to go right, or yep, this is going to go left. This is something that has to be experimentally determined. And there's a reference book that's got some of these values located on the inside, these positives and these negatives, and it kind of tells me going into it, like what are they going to do? So this is something that I don't necessarily have to figure out for myself, but it is something that I have to rely on other people doing those measurements for, so that way I know what to expect for myself when I make these measurements. So I can never look at a structure and tell you if it's going to rotate left or right-handed. That is not the way that it works. I can look at a structure and tell you if it's right-hand oriented or if it's left-hand oriented, but that right-handed oriented structure and left-handed oriented structure has nothing to do with the way that it rotates light. They are totally separate from each other. They do not correspond to each other. So I could have a right-handed molecule, whatever that means, right? And that's something I'm not necessarily going to talk about. That's more organic. But I could have a right-handed molecule, and that right-handed molecule, think of your right hand, that could rotate light right-handed, or right-handed molecules can rotate light left-handed. It just really depends on what they want to do. So that's a three-dimensional thing that kind of corresponds to this direction, but at the same time, that does not correspond to how it rotates light at all. So don't get those confused. Next up, not all samples rotate. And if they do rotate, they have to have something that we call a chiral center. And a chiral center is also known as an asymmetric center. So we're going to talk about that at least. We're going to define and we're going to look at molecules and some examples of chirality and these molecules that have a chiral center, because if it has a chiral center, then it has an asymmetric center. And if it has a chiral center, then yes, it's going to rotate light. And it's going to either rotate it left-handed or it's going to rotate it right-handed. Don't really know which one it's going to do, but it's going to rotate light. I just got to kind of go through the motions, putting onto the machine, making that measurement to figure out what it's going to do. Next up, there is a definition called an isomer. An isomer, mer means unit. Iso is kind of the same, just connected in a different way. Think of Legos. I can take a set of Legos and I can connect those Legos in a certain way and make something out of it, right? And then an isomer would be taking the same number of Legos and connecting them in a different way to make something that looks different. That is a isomer of the first one. I'm using the same ingredients. I'm using the same pieces. I'm using the same parts. They're just connected in a different way. So that is an isomer, and the number of isomers can actually equal 2 to the nth power, where n is the number of chiral centers. All right. So chiral centers, let's say I've got one chiral center, whatever that means. We've not talked about it, but let's say there's one of them. Well, 2 to the 1 power is 2. There we go. All right. So that means there will be 2 isomers of this molecule based on the number of chiral centers that it has. Okay, well, let's say that a molecule has 2 chiral centers. All right, so 2 to the nth power is 2 squared. All right, so 2 squared, 2 times 2, 4. That means 4 isomers that it can have. So there are 4 different ways that I can take those Legos and connect them together to make something different. In the other version, 1 chiral center, there's 2 different ways that I can take those Legos, connect them to make something different. The criteria, though, is that all the Legos have to be used. So every single piece has to be used in order to make something out of. All right, so there's a little bit of organic definition for you of chirality, asymmetric centers, and this term isomer, which just means pieces, building blocks that are connected in different ways to give you different molecules, but the same ingredients, right? So think of making a cake, and I've got all of these ingredients out: my eggs, my oil, my water, my flour, my sugar, my baking soda, my baking powder. All of those are ingredients that I have to use. And if I have to use every one of those ingredients just in a different way, how many things can I make out of that, right? I mean, okay, does a cupcake count, and a cake, or a brownie? You know, what goes on? The criteria, everything has got to be used. All right, so a little bit of chirality before we talk about chemical structure. Here are chiral and what we call achiral objects. And I think the achiral ones are a little bit easier to understand. So if I go down here to this achiral object, this looks like a bottle. All right. So here I have a bottle, and this is supposed to be a mirror. So I'm going to take the mirror image of it. If that bottle looks at itself in the mirror, and I take that image and I cut it out, and it's here to the side. This is the left-handed form, and this is the right-handed form. The image has been flipped. If I can cut this image out, and if I can cut this image out, and if these two things can overlay on top of each other and match perfectly, we call that they can be superimposed. So if they can lay on top of each other perfectly, then this is what we call an achiral object. So a bottle that is very symmetrical looking is an achiral object. Another achiral object would be just a ball or a sphere. So I take this sphere, this bowling ball, ping pong ball, basketball, whatever the case is, I take this up to the mirror, and I take the mirror image of that. If I take the mirror image of it, then this mirror image looks exactly like the original. And I can cut out that picture to the left, and I can cut out that picture to the right. And if I can overlap them on top of each other and they have a perfect overlayment, they are superimposed. So that means it's an achiral object. What this means is that achiral objects do not have chiral centers, of course. All right. Now, again, whatever chiral center means, Tracy's not told me what a chiral definition is actually supposed to be. And I'm not going to, not quite yet, but we're going to make it there. But I just know, simply based on the mirror image, if they overlay, they do not have a chiral center. That also means that these achiral objects do not have optical rotation. They will not show anything at all in a instrument or with this measurement that we're getting ready to talk about. So if I've got a molecule, and that molecule has a mirror image, and if I take those molecules and I cut out those mirror images and I overlay them on top of each other, and they can be superimposed, then that means they do not have a chiral center, and that means they will not respond to anything if I put it into a polarimeter that measures optical rotation. So these are the objects or the molecules that do not rotate light. Next up are the chiral objects. So here is my left hand, or somebody's left hand, right? And then we're going to take a mirror image of that left hand. And when I do that, I get kind of your right hand. So if you look at your left hand and your right hand, so if you just look at them in front of your face, the backs of your hands are faced forward to you, and you look and be like, oh yeah, these look like mirror images, right? I mean, here's my left hand, my 4 little fingers at the top, my thumb is over here on the right hand side. And then if I take the mirror image of that, it looks like the back of my hand is still faced forward, but my thumb is in an opposite direction. And there's no way that I can overlap my left hand or my right hand on top of each other to make them perfectly match. Now, I could get my fingers to perfectly match. So my thumbs will stack on top of each other and my fingers stack on top of each other. But in order to do that, I have to turn my hand around. So that means that one side of my hand, which is my palm, is faced forward. And on the other hand, it's the back of my hand. So they're not actually identical images. So no matter how you turn your hands, you're never going to be able to get to a point where they are perfectly going to stack on top of each other and make a perfect match. Something's always going to be oriented in a different way. And molecules are the same way, like your hands. There are some molecules that are left-handed in nature, and there's some molecules that are right-handed in nature. And if they have a left and a right hand, then this is something that we call a chiral object. And a chiral object has an asymmetric center. And a chiral object, ching-ching, has optical rotation. So that means that if my hand could be placed into a solution and placed into a polarimeter, that I could get a, well, no, we need to talk about molecules, not hands and balls and bottles. It just doesn't make any sense that way. So let's kind of take a look at chiral and achiral molecules. So if I take a look at the image over on the left-hand side of the screen, I'm going to look at the one on the far left. And here's a molecule. This center piece right here, it's not drawn, but there's a connection point right there that all 4 of these things go to. And that is going to be a carbon. It's understood to be a carbon. That's the way that organic works sometimes. If nothing is drawn, if nothing is written there, it's assumed to be carbon because it's a carbon-based course and carbon-based molecules. So in the middle is a carbon. And this particular carbon, look at this, has 4 things attached. It's got a hydrogen, and it has a chlorine, and it has a fluorine, and it has a bromine. So there are 4 different things attached to that carbon. And that is the criteria for a chiral center, or in this case, a chiral carbon. So we've got chirality here in this molecule. And we have a chiral carbon. And that carbon is in the center of everything. It's in the middle. It connects all of those pieces together. And the reason that this is chiral is because there are 4 different groups that are attached to it. Folks, this is how hard organic chemistry needs to be. It shouldn't be any more difficult than this, right? So if I take a look at that molecule and I see that center and I'm like, yeah, look, hydrogen and chlorine and fluorine and bromine, and they're all different and they're all 4 connected to that carbon, we've got chirality. And that chirality means ding, 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 we get optical rotation. And we get optical rotation because if we flip that molecule and do a mirror image of that molecule, if we did these 3-dimensional shapes with molecular structures, and I take these 3-dimensional shapes and I try to stack them on top of each other, and I twist and I turn them and I try to get them to fit perfectly on top, they will never fit perfectly on top because they have a chiral center. They're just like your left-handed and your right hand. This is a left-handed version of a molecule and a right-handed version of a molecule. No matter matter what you do to twist and cut out that image and try to stack them on top of each other, it's not going to happen. They will not perfectly overlay on top of each other. So because of that, because they have a chiral center, and in this case a chiral carbon, they have 4 different things attached. If they have 4 different things attached, then by default, we probably are going to get some optical rotation from that compound. So we clear it out and we say, yeah, if we go into the lab and we do optical rotation tests on this, we're probably going to find a number, and we can record that number and report that number. Over here on the right-hand side of the screen, you're going to see a couple of different options. Look at this. Here's a carbon in the center, and we get a hydrogen, and we get a bromine, and we get a chlorine, and then we get this CH3 group, whatever that's called. That's called a methyl group, by the way. So we get 4 different things attached. So 4 different things attached. Cha-ching! That's chiral, and cha-ching! It has optical rotation. That's what this is all about. All right. The next example, number 2, we have an achiral object. So here is the center of the carbon, and it's got to have 4 things attached. So it does. There's 4 things, but are they different? That's the key. So here we get a methyl group, and that's 1, and a hydrogen, and that's 2, and a bromine, and that's 3, and then oh, another hydrogen. So 2 hydrogens. That's not 4 different groups, because there's 2 hydrogens on this thing. So because of that, this is an achiral molecule. And an achiral molecule means that I could take the mirror image and I could cut out that mirror image, and the mirror images will stack on top of each other and match perfectly, which means no optical rotation, and I probably should not be running that into a polarimeter because I'm not going to get a number. Next up is another example, and in this example number 3, I see this carbon in the center, and does it have 4 bonds? And count them, 1, 2, 3, 4. Yes. Okay, so now are they different? And then I'll look at these and I'll see, oh, look, a little methyl group right there, and then number 2 is a hydrogen, and it's right there, and then number 3 is a carbon and a carbon and a carbon. I've got to take the whole thing, right? Even if I don't take the whole thing, this CH2 is different than that CH3, but really preferably you take the entire group. So CH2 and CH2 and CH3, this is what we call a propyl group in organic. Again, that's not important for us, but for those organic folks that are out there, that's what you're going to see, or that's what you've already been talking about. So that is different than the one on top. And then the 4th one is a CH2 and a CH3. So again, I got to take the entire thing. There's my 4th group, and that is different than the CH3 on top. That's also different than the CH2, CH2, CH3 on the bottom. This is a ethyl group, and that is a CH2, CH3. Again, the names do not matter here, but these are 4 different groups, and that's what's important. So 4 different groups, cha-ching, cha-ching, we get chiral, and that means if they take the mirror image and we cut out the mirror image and we try to stack them on top of each other, it's not going to work. So because it's cha-ching, cha-ching, chiral, then it's going to be cha-ching, cha-ching, optical rotation, which means cha-ching, cha-ching, polarimeter, and I should be able to make a solution of this molecule, put it in a polarimeter, get a value, and report that value. And then finally, in example number 4, this is a molecule, and it has a center, and there it is. And the number 1 criteria is 4 different groups, 4 bonds, right? 4 bonds. All right, so here's 1 number bond to the hydrogen. There's a second double bond to a CH3. And then here is a line and a line, but we got to count that as 1 because look, it just only goes to 1 thing up here on top. So this actually doesn't even have 4 bonds by definition. It has a double bond, and that double bond goes to 1 group, but there's not 4 groups that are attached to the center, and that's what this is all about. You've got to have 4 groups attached to the center, and this is regarded as the same group. So I get an oxygen, and I get a hydrogen, and I get a CH3 group. There's only 3 that are attached to that methyl carbon, and therefore this is a Achiral carbon. And an achiral carbon means I could take the mirror image and the mirror image matches perfectly. I can stack it on top of each other without a problem. And then it does not have optical rotation because of that. And then I probably don't want to run it in a polarimeter because of that either. I'm not going to get a value. There's going to be nothing that's going to happen inside of this instrument if I decide to make a solution and actually run it. Next, before I kind of leave you in this video until we come back next, I do want to say that we talk about optical activity and optical rotation. And if it's got optical rotation, I have been using a word, and that word is a polarimeter. And a polarimeter is actually what runs and measures these samples. So this is the name of the instrument that we will be using in order to obtain these values with. So if it has optical activity, because it has a chiral center or an asymmetric center, then we should be able to load that sample on a polarimeter, and that polarimeter will provide us a value. So in the next video, we're going to pick up from this slide. We're going to talk about a polarimeter, talk about the things that it can and cannot do, how does it do its job, what's actually going on the inside of that polarimeter, so that way we're going to be more comfortable discussing and talking about this test, and maybe performing the test, and being more comfortable when this is discussed and introduced in an organic chemistry class, if you're lucky to take one.